a region bounded by the curves a region bounded by the curves y equals x squared plus 3, x equals negative 1, x equals 1, and y equals 2. So you've been given 4 curves. So this is the first one, this is the second one, this is 3, and then this is 4. So you've been given the equation of all these curves, and you're told that the curves, they are rotated about the horizontal line y equals 1. So what you have here is your axis of rotation. So the axis of rotation, that's y equals 1. Now what we're told to do is we're told to plot the region and label the points where the curves intersect. Show all the points, or show all the coordinates of these points. So that's the first question. The next one says write an integral that describes the volume of the solid of revolution. Specify which method you're using. That is, are you using the vertical slice or the horizontal slice to evaluate your integral? And the last question says evaluate the integral obtained in part B. So again, there are lots of things going on in here, but we're going to do them step by each. So the very first thing you want to do is draw your x and your y axis. That's a very good starting point. So I'm going to start by drawing my x and my y axis. That's what I have here. So I'm going to label this as my y axis, and I'll label this as my x axis. So the next you want to do is you want to include all the curves, all the 4 curves you've been given. So the first one here says y equals x squared plus 3. So y equals x squared plus 3. So that's just going to intersect. It's going to intersect at this point here. So let's use a different color. So let's say this is point 3. So this is going to be my curve. So again, nothing fancy, just for illustration. So this is the graph y equals x squared plus 3. That's this graph here. That's the curve you have there. Then the next one says x equals negative 1. X equals negative 1. So negative 1 actually falls in this region here. So this is negative 1. So this is negative 1. Okay, again, nothing fancy. So this is negative 1. That's the whole of negative 1. The next one is x equals 1. That's x equals 1. So again, we'll go. So x equals 1 falls in this region here. X equals 1. So you have this like that, and then you have stuff going up here, you have stuff going up here. And then last one says y equals 2. So y equals 2. So this is if this is 3 and then this is 0, so probably let's say this is just going to be 1, and then this is just going to be 2. So y equals 2 is what you have here. And then you have something going here, you have another one going on here. So so this is the graph of y equals 2. This is the graph of x equals 1, while this is the graph of x equals negative 1. So we have all the 4 graphs here, 1, 2, 3, and 4. Let's go back to the question. It says it is rotated about the horizontal line. Now, since it is rotated about the horizontal line, so that tells me y equals 1 is the axis of rotation. So y equals 1, that's going to be my axis of rotation. So I'm going to denote that with dotted lines. Y equals 1. So in other words, the region is going to be rotated about this. So it says plot the region. So let's thicken out the region. Now from what we see here, you can see that all the curves I drew, that is 1, 2, 3, and 4, they bound this region here. You observe that they bound the region we have here. Yeah, so this is the region they bound. So we've plotted the region. Label the points where the curves they intersect. Now to label the point where they intersect, so you can see they intersect at this point, they intersect at this point, they intersect at this point, and also at this point. So how then do I find the coordinates of those points here? Now, corresponding to this point here, so what you have here is, probably I should use something darker. So what you have here is your x equals 1, so that means the x coordinate here is 1, and then your your y equals 2. That is for that. And also for here, the coordinates here is going to be the x equals -1, while the y equals 2. So we are done with these two. So let's go to the next one. Now for this one, the ones that we have here, again your x equals 1. Now how do I find the y coordinates? So we're going to use the formula that we have here. So when you plug in 1 into here, you have y equals x squared, which is going to be 1 squared plus 3, and that is 4. So when x equals 1, y equals 4. And then similarly here too, when you plug in, it's still the same formula. When you plug in -1 in here, you have y equals -1 all squared plus 3, and this will give you 4. So again, when x equals -1, our y equals 4. So we have labeled all the points. So again, you can see you have all the 4 points, they've been labeled. So that tells me that this point here should be 4. Let's go back again. Plot the region. We've plotted it. Label the points where the curves intersect. We've labeled that. Show all the coordinates of the point. We've done that. The next one says write an integral that describes the volume of the solid of revolution. Now, we've been told that the curve that we have here, the region that we have here, is rotated about this point here, about this axis of rotation. So since it's rotated about this, so it implies that the axis here serves as a mirror. So again, there are lots of things going on in here. So the whole thing is spinning around this axis. So it's going to have a replica. Let's say the exact distance. So if this is 1, this is 2. So it's going to start from here. So let's say this is the image of this region here. The image is just going to be somewhere here, and then you have this. So basically this is what you have. So we're told to find the volume of the solid of revolution. So again, and then it says specify which method you are using. So we're going to be using the vertical slice. So we're using the vertical slice. So again, to do problems like this, we would continue what we said we would do. We start by slice. When you slice, you sum, and then you would integrate. That's all you do. You slice, you sum, and you integrate. So I'm going to start by creating a slice. So let's just pick a slice here. So let's say this is my slice, and my slice here, I'm going to call what we have here, let's call the length. The change here, we'll call the change here delta x. So it intersects at this point here, and it also intersects at this point here. Now when this whole thing here is rotated about this the line y equals 1, it's going to form a cylindrical shape. So let's bring out the shape. So when you bring the shape out here, so this is exactly what you have. You have something like this. You have something like this, and then you have this. So this is what you have. So let's assume this is the middle. Now when you look at this, when you look at the slice, you'd observe there are certain things going on here also. Now you see that there's a hole here. Now because there's a hole, so that tells me my cylinder is just going to also have a hole. So it's going to have a hole. So how do I find the radius of the inner radius, and then how do I find the outer radius? Well, if you look at the problem here, now look, what you have here is 1, and what you have here is 2. So to find from here to here, this is going to be my inner radius, that is my r in. It's just going to be the difference between 1 and 2, and that is 1. While the outer radius, so in other words, I found my inner radius, that is my r in, equals 1. Now how do I find the outer radius? That is, I want to find from here to here. Again, what you'd observe is that the function itself, that is the graph itself, the graph from here to here is from here to the x-axis, and that is x squared plus 3. That is the graph itself. But then the distance from here to here, you know, this is 1 and then this is 0, so that tells me distance from here to here is going to be 1, right? But what we are interested in is from here to here. Now if from here to here is x squared plus 3, and then this is 1, this is x squared plus 3, so to find the remaining part, I'm going to deduct 1 from this, so that's just going to be x squared plus 3 minus 1, and that is x squared plus 2. So in other words, the length of this is x squared plus 2. So that tells me that my outer radius is actually x squared plus 2. X squared plus 2. So now we are done. So I'm going to find the volume of the cylinder, which is part B. So the volume of the cylinder, of this washer, is actually the volume of the outer, like we did in the previous question, minus the volume of the inner cylinder. So, and then the formula for the volume of the outer cylinder is pi times r square, then times the change in x. This is my delta x, minus pi times r in squared times delta x. So this is just going to give us pi. Now my r out, this is my r out here, which is x squared plus 2 all squared minus my r in. My r in is 1 all squared, then multiplied by delta x. So this is what you have. Then the next thing is you want to find the total. That's the total volume. Let me call that the total volume. That's just going to be the sum of what you have here. That's x squared plus 2 all squared negative 1 squared delta x. And then to find the exact volume, that is the exact volume, so what you have here changes to an integral sign, and then you have pi multiplied by x squared plus 2 all squared negative, now 1 squared is 1, and then this also changes to the x, and then my x runs from where to where. So again, you see my x is just going to be running from, so you can see there are lots of things going on in here, so it's just going to run from here to here. So it's running from negative 1 to 1. So my x runs from negative 1 to 1, and when you evaluate this, so this is just going to give you 136 pi divided by 15. So this is your final answer. So let's go back again. Write an integral that describes the volume of the solid of revolution. So this is the integral that we have here, and then B says evaluate the integral. That is B, evaluate the integral. Now when you come here, this is our evaluation. So that completes the problem.